Welcome to part 2 of the lacrosse helmet. There are plenty of surfacing techniques left to come. Anyway, so now I take this and split that face again. I just use a straight line and split it right here. And I delete all the faces in the back. Okay, now what I'm getting ready to do is kind of the point of most of the exercises in this model. It's to blend in a couple of shapes and make something that has hard edges blend into something that's smooth. So I'll get this boundary surface, and I can loft this boundary surface from that edge on that extrude feature to this edge on the face of the finished model. And that allows me to get that blend. This boundary surface, you notice, doesn't have any features under it because I'm just using model edges. In this case, I'm not using any sketches at all. These two edges are selected, and the curvature constraint is used for both of them. One thing you have to make sure of is that your surface doesn't get tangled up with the main surface as it goes underneath. I use these two surface fills to fill in these side gaps. Most of the time when I do things like this, I'll take some point and knit a bunch of surfaces together. Why is that important? It's important if you're going to manufacture this thing and you want to actually make a mold. You don't want to send the mold maker just an accumulation of faces. You want those faces to be joined together into a single body. And in fact, eventually, you'd probably want to make a solid body out of this. Making a solid is really just proving that your geometry is good. Watertight, manufacturable. It's not a figment of your imagination. It's really possible in the real world. Knitting together surface bodies into a single surface body is a step towards that. It's tempting very often to knit something together and then make a solid out of it just to test it. And then you tear it apart again, and then you have to knit it back together. So you'll know if a model has a lot of thicken features in it, or knit features that knit a surface into a solid, you'll know that there's problems with that model, because if you're going in and out of surfacing a lot, it's very inefficient. It's best if you can just work in surfaces until that area of the model is done and it's ready to be made into a solid. So, in fact, this model never actually makes it into a solid. We don't have to worry about that here, but that's something that with your production models, you're going to have to pay attention to. Okay, let's look at another trim. Another trim here. We've got a section knocked out of the top of the helmet. All right, this is another what I call this is a reference tangent surface. So I'm going to close this gap in, but down at the bottom here, I did this with sketches. Here I'm doing it with an extruded surface. Is there any difference? Yeah, there is. I think on a sketch, the best you can get is a normal 2 constraint when you're creating the boundary surface. But on a surface like this, you can get a curvature continuous constraint. Curvature continuous to an extruded surface is going to start out with 0 curvature because an extrude has 0 curvature. But curvature continuous to a curved surface is going to be a different situation. Let's take this and hide it because we don't really need to see that. And then we knit that together. So we're just knitting these two surfaces. And then, you're going to see a pattern here. We do a trim. We do some sort of an extrude to create a reference surface. And then from there, we create a boundary surface. you notice that my reference extrude in this case didn't touch the other side. And that's because I'm making a gap there, and that gap is filled by the second boundary surface. And this is essentially just another vent that goes on the back of the helmet. After that vent, we're simulating that thickness of the plastic with this boundary surface that was put in. After that feature has been built face by face, we knit it together into the main surface. And you notice that that some of my edges here are looking nice. Like this edge has a line font on it, what they call a phantom line font. This is because I have a setting in Tools Options Display, and here Part Assembly Tangent Edge Display. Default is set as visible, but I like to use as phantom, because that means that I can know that if this edge is tangent, it's going to show up already in this special line font. If an edge is sharp, like this one, then it's going to show up with that solid line. Another thing that I want to point out here is that you notice down here, this feature was created from a sketch that had a break between entities. So this is a spline, and then this is a non-tangent spline, or those could be arcs or whatever they are. So the point is that they come together at a point, and they create a hard edge in the model. If you look at the way this was done a little differently. This extrude, this is made differently, so that this is a single spline that goes across, and instead of a sharp edge, I've built the fillet right into this. So this is smooth. These are two different ways of creating the same sort of thing. Later on, I'm probably going to have to come down here and struggle with getting a fillet across this edge. Okay, same thing here. Because, getting a fillet to taper down to nothing and to go across another edge like this, that's taking a risk. But I can tell you that doing something like this is a little cleaner. In fact, it's a lot cleaner, and it's not taking as big a risk with that fillet. So 2 different ways of doing things demonstrated on similar features. Thanks for watching part 2 of creating the helmet. Stick around for part 3, where we'll talk about the ruled surface and other finishing details.